intermediate mass black holes, which are small compared to, say, an 87, but they are still powerful. And after this talk, I think you can see that this is also a very good description of Jenny. So today she will tell us about this brand new view of IZ AGNs as revealed by JWST. Let's welcome Jenny.
Thank you, Yenting. It's really a pleasure to be here. It's a pleasure to be in Taiwan, and I'm super excited to tell you a little bit about the wild ride that JWST has been for me and how it's really changed my life in all the best kind of ways. So this is work that I've been doing as part of the Uncover collaboration, which is led by Ivo Labe and Rachel Bazanson, and in the background is the Abell 2744 field that Uncover is in. So we'll talk about all that, but by way of motivation, this is an AGN talk. This is about the growth of supermassive black holes at early times. And, harkening back to my thesis time, in the early 2000s, we were just learning through amassing large samples with HST that supermassive black holes are indeed ubiquitous at the centers of massive galaxies. And of course, astronomy got the Nobel Prize for the very accurate and very precise black hole mass at the center of our own galaxy. And of course, we also have imaged the event horizon for two local black holes, our own, Sagittarius A star and M87. But a big question that I have devoted much of my life's work to has been, how did these supermassive black holes form in the first place? And we don't think that billion solar mass black holes like M87 harbors pop out of the ether like that. We think they started smaller and grow, but we actually don't really have a good picture for how they grow. The most certain astrophysically for sure would be the death of massive stars, since we know that black holes form in the death of massive stars. But we are seeing billion solar mass black holes only a few 100 million years after the Big Bang, and force feeding the 100 solar mass seeds to be that big is very challenging, if not impossible, depending on how you feel about super Eddington accretion. And so there's a whole family of models in which you don't go through a stellar phase. Instead, you manage to find gas with low angular momentum that doesn't fragment, that has just the right level of UV background to make maybe 10 to the 4 solar mass black hole seeds. All the models that do this make very low number densities, nowhere near enough to explain the whole black hole population. And so there's a third class of models in which you make clusters of stars, and those, you have dynamical interactions at the centers of these clusters, which either make supermassive stars or later black hole mergers happen, and you could have 1,000 to 10,000 solar mass seeds form at the centers of these star clusters. So those have been our stories. And of course, as we find more and more very massive black holes at early times, you get pushed into these very uncomfortable situations in terms of whether you want to grow your black hole faster than the Eddington limit, or you want to start your seeds more massive. And so this was sort of the state of play for known accreting black holes at high redshift pre-JWST. And just to drive home this point in terms of numbers, this is basically the whole sky, a few hundred quasars with redshifts above 5.3. Now, I never paid attention to high redshift quasars. I thought reionization was boring. And if you're like me, you may not have appreciated, I still think reionization is boring, that hasn't changed. This is the luminosity function for high redshift quasars, UV selected, ground-based UV selected quasars. And what you can see is that the number density does not rise at faint luminosities. So here are the galaxies, here are the quasars. The number densities are way too low. And so unlike every other redshift in the universe, it seemed like, pre-JWST, it seemed like most galaxies did not yet have a well-developed black hole if we thought we were finding most accreting black holes with the UV and the X-ray. So that was the situation. So that's one of the contexts in which we started our JWST work. The other context was one of the very, very first results from JW was that people just started finding redshift 10 to 12 galaxies way faster than they had anticipated based on extrapolating luminosity functions from pre-JWST. So we seem to have too many galaxies, and we seem to have two massive black holes. And this problem is just getting more interesting as we continue to get JWST data. So here's one of our favorite record holders. This is a galaxy which seemed to have formed most of its stars between redshift 8 and 10. So we're observing it at redshift 5, but it does seem to potentially be the descendant of one of these very, very early star-forming things. So to assemble 10 to the 11 solar masses of stars at that epoch seems rather extreme. This is also just an incredibly beautiful spectrum. This is JWST prism. So we're talking about R of about 100 here, and we see the Balmer absorption lines quite clearly. So this is a stunning, stunning object. Right, and so in 2022, on the archive, Ivo Labe put these objects, and then I'm going to show you a lot of SEDs that look like this. So this is NIRCam imaging from 1 to 4.5 microns. So just the 6 broad bands and then 1 medium band here. And what you see is you see a Lyman break. So that places these galaxies at redshifts above 6 in this paper. And then you also see a second break here, which looks like it may be a 4,000 angstrom break. And so if these things are at redshift 7 to 8, and what we're seeing are Balmer breaks, evolved populations at redshift above 8, so these were claimed to be 10 to the 10 to 10 to the 11 solar mass galaxies at a redshift of 8, which seems it's an impossible thing to make, just given what we know about how many dark matter halos there are. So the number density of these things was claimed to break CDM, and my family was calling me and asking me if the universe was broken. So this was another sort of exciting early development with JWST. So we have these two tensions going into my work that I want to talk about today. And not enough black holes compared to galaxies, but too many galaxies. And so that's the framing for this Uncover survey, of course, which was doing many, many things. This is a Cycle 1 Treasury program, and I just want to highlight some of the junior people that did incredibly heavy lifting to make the catalogs and make the survey go forward. Sedona Price, who's a postdoc with Rachel at Pitt, John Weaver with Kate at UMass, and Bingji Wang with Joel Asia at Penn State. Okay, so Abell 2744 is a redshift 0.3 lensing cluster. It's a Hubble frontier field, and this is the Uncover imaging. Again, it's about 4 hours for each of those NIRCam bands plus the 1 410 medium band. And of course, I'll tell you, the Delta people, they have really, really nice screens. But no astronomy screen that I've shown this on completely does justice to the data. So I highly recommend when you're having a down day at work that you Google JWST Uncover and just look at our images. They're absolutely gorgeous. And we get to 29th magnitude. So for us, 27 is bright. And so it's just really a ridiculous change in data quality. So, these are the cluster galaxies and their intracluster medium, which of course Yenting is an expert in, and then all of these lensed galaxies and just all kinds of fun stuff happening in these pictures. It's just wonderful. So this is our coverage of Abell 2744 in imaging. So we did the imaging in October of 2022, and then we had 8 months to analyze the images and then pick spectroscopic targets, the spectroscopy with the NIRCam prism. Again, this low resolution, wide wavelength coverage prism was all completed in August of 2023. We also have deep ALMA data. This was done by Seiji Fujimoto at 1.2 millimeters, and that has turned out to be a really important resource. So either the first or the second uncover paper was on this object. Here, this is a triply lensed red source at a redshift of 7. It's extremely compact, so it's a point source magnified by a factor of 6, which limits its size to less than 30 parsecs. And it, again, has this very strange characteristic SED, rising in the rest frame optical, so very red in the rest frame optical, and then some UV. So very reminiscent of these double break objects that were breaking the universe in August of 2022. And so in this original photometry only paper, we did try to fit a bunch of models, but I'll tell you what, galaxies don't really do this. It's extremely red. And so in this particular case, it wasn't really plausible to fit this as a 4,000 angstrom or Balmer break. And then you need to invoke a second component to explain this UV. Because it was so compact, already in this paper we were saying the most likely explanation for this thing is that it's an accreting black hole reddened by dust. So that was the story. And we thought, well, why don't we try to look through the uncovered data and see if we can find more. And so we just did a red selection. So this is 277 minus 444, redder than 1, and then a second band to make sure that the red color is not just due to emission lines, that these are really red continua. And then we did a size cut to make sure that these things were compact. And so here you see they're very compact and they're very red. And the uncover field is about 40 square arc minutes, and we found 30 candidates. So their number densities are quite high. So what do we do with these SEDs? Again, steep rising red continuum in the rest frame optical and a little dusting of UV light. So you can model this thing. If you allow yourself 2 components, you can pretty much model it however you want. You can have dusty star formation explaining the red continuum, and then just a little bit of the star formation peeks through to explain the UV. In that case, you have to deal with the fact that it's very compact. You can, in some cases, fit the thing as an evolved, very, very compact, very evolved, massive galaxy. Or our preferred solution at the time was a reddened AGN, so the intrinsic accreting black hole is the red part, so there's a lot of, AV of 2 to 4. You can see the broadline region, but it's quite dusty. And then a little bit of scattered light. So objects like that have been seen. These were the different ways we modeled the photometry in this Labe paper from 2023. Invoking the ALMA data actually made a big difference, because if this were all dusty star formation, then we should actually see a booming signal at 1.2 millimeters, presuming normal dust temperatures of 25 to 30 Kelvin, whereas we have only upper limits in the ALMA. And so we deprecated the dusty star forming model in preference for the AGN model based on the ALMA observations. Around the same time, we were not at all the only people to be finding these compact red sources. Yorit Mathi and Rohan Naidu had a sample from Fresco, and this is a grism survey in Goods North and South, and what was important here is that they actually had spectroscopy. And so here are these compact red sources, which they named little red dots, and that name has now stuck. And in this case, you see prominent, broad H-alpha. This is broad Balmer lines, which really, 2,000 kilometer per second lines, really suggests motions around a supermassive black hole. And so our paper and their paper came out last summer, and we thought, okay, we figured this out. These are accreting supermassive black holes. But then we got the uncover spectra, and the universe was extremely kind to us. So this is, again, the triple lens source. And now you're seeing the prism spectrum from uncover. We did put a mask on each of the 3 sources. So 38 hours on source with lensing. We called this a 1700-hour JWST spectrum that sold it to nature. And so anyway, in red, you can see the photometry, and in black, you see the actual spectrum, and you see this is just an incredibly weird spectrum. So we do see Lyman alpha, we see H beta, this is H alpha right off the edge of the spectrum, and we see almost no metal lines. So this is where O3 would be. It is detected, but extremely weak. The H beta is quite broad, and so, we said, dusty, growing black hole in the early universe, and that was our first spectroscopic little red dot paper in the fall of 2023. This was all of the spectra. So we put MSAs on 17 sources. 3 of those were one lens. 3 of them were brown dwarfs, so beautiful brown dwarf spectra. Not our intention, but there you go. And almost all the rest of them showed clear and unambiguous evidence for broad H-alpha at prism resolution. So this is 2,000 to 4,000 kilometer per second broad lines. So there's our lensed friend again. And again, you see this characteristic rise, red continuum, a little bit of UV, but there were other gifts as well. So this is a redshift 8.5, broad line AGN, so one of the highest redshift known broad line AGN. And this is one of our absolute favorites. This thing is 22nd magnitude at 444, so it's incredibly bright. It's a 10 to the 9 solar mass black hole, if you believe these broadline scaling relations. And again, what a 10 to the 9 solar mass black hole is doing in a 40 square arc minute field, you know it. When I first plotted this, I was like, okay, what did I do wrong in my code? That seems way too big. Yeah. I'll also note something that I'll come back to later, that we wouldn't have been able to figure out from the photometry alone. You see this very characteristic break at around 3,600 angstroms, which looks an awful lot like a Balmer break. And indeed, most of the sources do have their spectral slopes change right around that wavelength. So I don't know why I came back to that, but here. Photometric selection issues if you're interested in the really nitty-gritty details. So compared to that original Labe 2022 paper, the double breaks. Oh, you all right? Okay. This is again this red color 277 minus 444. 30% of such objects that would pass the universe breaker criterion, 30% of those at least have broad Balmer lines based on our follow-up spectroscopy. This is the entire uncover sample. We learned that it's easy, in fact, to exclude brown dwarfs because they are bluer in 115 minus 200 than any of our AGN. And then if you add the compactness and the second color, then more than 80% of our uncover little red dots turn out to have broad lines. So very suggestive of accreting black holes. All right, so why am I giving you this talk? Why do we care? The answer is that the number densities are very, very high. So remember, I said that the UV selected quasars are quite rare compared to galaxies. These are the galaxies, these are the UV selected quasars, and these are the little red dots. So they're much less luminous in the UV because, as I showed you, they're very, very red. But they're 100 times more numerous than UV selected quasars, and they account for something like 3 to 5% of the galaxy population and at least 20% of broadline selected AGN from JWST. And we're not talking about wimpy sources. So these big red stars are my uncover broadline objects. Their bolometric luminosities are approaching those of the faint end of the UV selected quasars, which are these open gray circles. And their black hole masses are, 10 to the 7 to 10 to the 9. So they're quite healthy. These are not really tiny black holes. These are pretty healthy black holes. We selected them to be point sources with JWST resolution, which means that there's just a limit to how much stellar mass you can fit inside these things because they're smaller than 100 parsecs. So if you just assume that magically every little red dot has a maximally dense stellar system, then the black hole mass is accounting for 1 to 20% of the mass of the system. So much more mass in black hole to galaxy than we see locally, where the ratio is more like 1.1%. So that's shown here. This is Vasily Kokorev's paper about the redshift 8.5 source. This here, the teal square, is the triple lensed friend, and these are local relations.
For the maximum impact stellar population, you are talking about the very central region, right? Because your observation do not cover res frame near infrared, so there can be a much extended stellar population that's thus extinguished.
Well, but then you'd have to extinguish the AGN too, right? I see a broad line AGN. So you want to just put the dust in the outer part of this large extended galaxy?
It's not possible?
I mean, it's possible. I would love to have some MIRI data. But we are getting well beyond the 4,000 angstrom break. I mean, I'm observing it rest frame 6,000 angstroms. I have H alpha. So, you really, that would be very dusty, and I still have to see the broad line. So I'm not saying it's impossible, but it's really contrived to do that for every single one of these sources, I would think. I'm sure I can be missing maybe even easily a factor of 10 in stellar mass, perhaps, but these are, if we believe the black hole masses, they are quite overly massive compared to their galaxy. Also, to grow almost 10 to the 8 solar mass black hole at redshift 8.5, again, you either have to invoke super Eddington accretion or you have to start with a pretty massive seed. Yeah, and so that's where the little red dots live. Very, very high black hole mass to galaxy mass. But I would argue that we don't really know the black hole masses. And in fact, depending on who you ask, these things may or may not be powered by accreting black holes. And I'm going to tell you some of the confounding evidence that keeps us up at night and why it has simply been elusive for us to understand the nature of these sources. So first of all, just trying to put the number densities in context. This is now, instead of a UV luminosity function, this is a bolometric luminosity function, assuming that that red continuum is indeed dust-reddened AGN. So that under there is a normal accretion disk, peaking in the UV, and then it's got an AV of 2 to 4 in front of it. This would be their bolometric luminosities. This is the higher redshift bin, so redshift 6.5 to 8.5. If you imagine putting an accreting black hole into every halo you have available to you at redshift 7, this is the bolometric luminosity function that you expect. So it is higher than what we observe, but is getting uncomfortably close. If you assume that the underlying galaxy to black hole mass ratio is the same as the present day, and you just add a little bit of scatter. This was Marta Voluntari's 2017 models. Nowhere near enough, high enough density of accreting black holes. She can, with the same semi-empirical model, reproduce our number densities, but she has to add, 0.5 dex of scatter to that underlying local relation. And this is assuming that all accreting black holes at these redshifts are little red dots, which they are not. And so the number densities are really getting uncomfortably high if you want to preserve the nominal black hole to galaxy scaling relations. But then we also really have some problems with the SEDs. So here is the standard lore. If you are raised as an AGN person, you believe that all AGN will do the following things. They will all have an optically thick, geometrically thin accretion disk, which peaks somewhere in the UV. Sometimes you can't see it because of dust, but it's always there. And then there will be some parsec scale hot dust that absorbs some of those UV photons, maybe a third of them or something, and re-emits in the mid-infrared. And so there classically has always been assumed to be this hot dust component, and in fact many AGN samples are selected based on this mid-infrared hot dust. And finally, we have always believed that the X-rays are the hardest to absorb, and so if you want to find the cleanest samples of accreting black holes, you will look in the X-ray because they can penetrate lots of dust, and only very Compton thick things can have their X-rays totally absorbed. So what's the situation with little red dots? Well, none of them has hot dust. They are completely flat in F-nu beyond about a micron. They look like either the extension of a bare accretion disk with no hot dust, or like a somewhat evolved stellar population, which is what Christina Williams has overplotted here in red. So this is for a stack of photometrically selected little red dots from JADES, but Vasily finds the same in his much larger sample of photometrically selected little red dots, and every spectroscopically selected object that we have with broad lines and MIRI also is completely flat in F-nu beyond 1 micron. We just don't see the hot dust out to about 5 microns rest frame. That's about as far into the red as we've managed to get. So we're still sort of hoping that there's a hot dust component, but that there's so much absorption that it's self-absorbed. And so that the hot dust is there, but it's going to come out and further into the red, but we can't prove that. So no hot dust and no X-rays. So this is redshift 5. So negative K correction means that we're looking at rest frame 40 keV. Very hard to get rid of X-rays at 40 keV. When you say Compton thick, you have to be really, really Compton thick. And so this is a stack of all little red dots in the Chandra Deep Field South, 7 megaseconds. There are no X-rays from little red dots. So much for everything that we knew about AGN. These have very broad Balmer lines. The easiest way to explain them is that they are orbiting a supermassive black hole, but there is almost no other wavelength in which we can find evidence for said supermassive black hole. Here's just another example. This is from Anna de Graaf's Ruby's program. So this is one of their first little red dots. There's a whopping broad line. She also has higher resolution grading data. So we know the broad line width very well. And there's the MIRI observation. So sorry, this is now F lambda, but it's totally flat in F-nu. And then finally, why, whenever we select these things that are compact and red and have broad lines, why do they also have prominent Balmer breaks? So these are the 2 Balmer breaks that I showed you from the really high signal to noise uncover spectra. But here's a stack of 3 more of the original universe breakers that Ruby's followed up, and you see that there's a very clear signature of a Balmer break, and all three of these have prominent, broad, really broad, Balmer lines. So this is Elon Ma. He's a spectacular graduate student at Princeton. He thought he was going to jointly model the AGN continuum and the galaxy continuum in a month. He started this in February, and almost daily he sends me emojis, and I tell him to calm down, Elon, it's going to be fine. But we have not managed to fit this, so this is the triple lens spectrum again. You see how very nicely it is fit by a Balmer break, but here this thing is 30 parsecs or smaller. And so this is starlight, we think. And so this is one of these cases where just to fit the spectrum, we need to make this thing maximally dense. So few times 10 to the 9 in stars, less than 30 parsecs in size. That's as dense of a stellar system as we've ever seen in the local universe. And then you got to make the AGN completely shut off so that you don't wash out the break. So it's kind of an impossible situation. Either you have a dust law, which 100% truncates your AGN miraculously, right where the Balmer break is. Or here we're invoking rather hokey super Eddington models, which pushes the peak of the accretion disk to the red and also allows us to fit the spectrum. Could the broad Balmer lines be something other than an AGN? Maybe that would solve our problem. Maybe these are not accreting black holes. We don't see them in the X-ray because there's no accretion. Maybe they're 1,000 supernovae. Or maybe they're Raman scattering. I don't know. This source, this is my friend the monster, has 10 to the 44 ergs per second in the broad H alpha line, which is 4,400 kilometers per second wide. I have struggled to come up with any other physical process that could make that line that is not super, this is naturally explained as an accreting black hole. So this source alone makes me continue to be confident that despite the fact that we cannot find them in the hot dust and despite the fact that we cannot find them in the X-ray, that there is an accreting black hole there. But I would love to hear other ideas because we are losing our minds.
Our Sagittarius star circumstellar disk at the center at a parsec. Wouldn't you get similar velocities and no black hole that's visible in any other band?
So you could get that virial line width at 20 parsecs, but you would end up with an unphysical amount of stars interior. I mean, if you want to put it at a parsec, you need the mass to be in stars, right?
Understood.
It would be an unphysical amount of stars, but there's another problem. I need to photoionize 10 to the 44 ergs per second. Where are the UV photons? All from stars. So now I'm doing thousands of solar masses a year of star formation in 20 parsecs. I don't think it's feasible. No, it doesn't do that. Our galactic center does not do that.
If you top up the black hole mass to 10, that is a 6 solar mass black hole, you do the 10 to the 9, and multiply everything by 1,000.
Yeah, but you want 1,000 solar masses of solar masses per year of star formation within 20 parsecs?
Well, but if you take our black hole, multiply by 1,000, you get 10 to the 9 solar masses in the black hole, and everything else up back of 1,000, and that's kind of what we have.
Yeah, but that's not physical. You can't do that much star formation in that small of a space. The thing would explode. But we have to find, there are 30 of them. I mean, the number densities are so high that if you make them that dynamically unstable, you have to be making them all the time. So I don't think that works.
They're not unstable if they make up 1% of the total mass. Black hole.
It would be in the sphere of influence, but I don't think that helps you because it needs to be UV photons enough to photoionize all of that H alpha. And that thing is going to just explode. I mean, from the photons from the star formation, I think.
We've got S stars in our galactic center that are like these Wolf-Rayet stars that are any amount you want. They're highly overrepresented. The abundance there is 1 million times higher than elsewhere in our galaxy.
Yeah, I mean.
So I'm just thinking nearby, right? Just back in our backyard. understood. It's 1,000 times more mundane than
I don't.
see,
I just
but
don't.
if you multiply by 1,000. It's not that different, isn't it?
I just don't think we have any object with that kind of mass density anywhere in the universe. Certainly not in the center of M87, which is also a 10 to the 9 solar mass black hole.
No, I agree. It's not doing it, but if you just saying.
You got to get rid of all that mass if you want to do it that way after you've made it. So I don't know. I don't think it'll work, but maybe someone will make it work. One opportunity that is very exciting is we should be able to measure dynamical masses with ELTs for these things. At least my monster at 10 to the 9, we should be able to get to twice the sphere of influence. This is a GMT specific slide because I made it for GMT. So it will be expensive, but in something like 35 hours, we could credibly do it. So maybe then we will find that it's not a point source. I don't know. We're out of ideas. I'm happy to consider anything. All right. So this is the summary of the problem. We have characteristic, very red spectrum, dusting of UV, very compact as 30 parsecs, as small as we can see. They're that small. We seem to have high black hole to galaxy ratio, although I would take the black hole masses with a great grain of salt because we do not detect them in the X-ray and we do not detect them in the mid-infrared, so we do not understand the SEDs of these things at all. So we've sort of already dove into the various musings that we all have about what could explain these objects. Maybe you can get rid of you have an AGN, but you can get rid of the X-ray with extra broadline region clouds, which maybe can eclipse the X-ray, but let the broadline region get through. Maybe you have all of your supernovae in the galaxy go off at once. Maybe that could power the broadlines. Maybe they're tidal disruption events or super Eddington AGN. Wave your hands. Maybe you can get out of these SED problems. But so far, no one of these pictures has seemed satisfying to explain everything that we observe and have the number densities be as high as they are. So I will leave it there and take questions.
Thank you very much.
And I'm not quite sure what you meant by super Eddington AGNs. So anybody who pushes super Eddington AGNs would argue that there is a non-radiative phase where I think the basic picture is that the inflow is just optically thick and carries everything with you, so you
Right.
don't have anything problem.
Right.
The problem
Right.
exists. Now, if you have this black hole in that phase, then you don't see any of the X-rays. So all the thing you're calibrating against are these naked I'm going to call them naked black holes that actually have this thin disk, geometrically
Okay,
optically
naked
thick
except for their disk.
Well, naked meaning that there's a black hole. Unlike one of these super Eddington black holes, those are dressed. Nothing's coming out, right? So there you see nothing. I mean, otherwise, they wouldn't be super Eddington, right? If something comes out, then you've got a problem. So any super Eddington, anybody who is willing to entertain it will say, okay, then there exists an accretion mode where things go in and nothing comes out. It's just it's really a black hole. That's what super Eddington. That's what those people mean. In which case, wouldn't you think be potentially evidence that you have now found this class of objects that is super Eddington accreting, and therefore you don't see any of these disks or reprocessing or dust because they're super Eddington. They don't expect to have them.
Well, so I talked to Yanfei Zhang, who's one of the people who has managed to have super Eddington accretion in his MHD simulations. My understanding is a little different from what you described. I mean, I have heard lots of theorists say when these seed problems are discussed, oh yeah, in the super Eddington phase, it'll be completely buried, no photons will get out, it'll be too red, and they'll grow, we won't know about it. So certainly people talk about that. But I think that in Yanfei's simulations, it's much more orientation specific, and you do have radiation in certain directions, and then you have sort of shielding allowing super Eddington in other directions. there's also the possibility, I mean, I'm totally waving my hands, right? But there is the possibility that you have partially a thin disk and then you have some advection that happens inside of it. And I think a lot of the slim disk models look like that. So there are UV photons, but there are fewer UV photons and the whole thing looks redder. So that's the SED that we're using. So there are indeed some photons that come out. There is indeed a broadline region of some sort, but nobody really wants to hand me a super Eddington SED, right? It's just, I don't think the theory is that well developed that we could actually fit these things. And we really do need a lot of UV photons, bluer to 13.6, just to ionize the broad lines that we see. So we can't get rid of all of the UV. You can get rid of a lot of X-ray in these super Eddington models, as you say. So that piece would be taken care of.
That's a long way away from black hole. So instead of stuff going around far away, it's just most of the energy comes out close. So all the UV or the X-rays, they come from close, and that you can hide. You can, meaning, I'm just not saying, in the grand scheme of things, you say, why do black holes seem so massive so early in the universe? I would have said, one of the possibilities is super Eddington. That's not a
That's right.
That's not a trivial opportunity.
Right.
And then you can ask, okay, if that is one of the paths, what should you be looking for? And maybe you should be looking for these little red dots. I mean,
maybe. I mean, a lot of problems.
This is not interesting, not predictive. Maybe you should look at and say, here is a path that connects all the dots. Sorry, that connects
all the dots. Yes, all the dots. No, super Eddington has lots of.
Understood. It's not a very precise predictive theory, but that tells you nothing.
No, but it solves a lot of problems.
Exactly.
It solves a lot of problems.
Indeed. And if this is, these.
Absolutely. I mean, if they are even just a little bit super Eddington, then the number density problem goes away. The overly massive problem goes away. I'm very happy with that, except for it is not at all predictive, so I don't know how to test it at all.
That's a big issue with the super Eddington. It's not that anybody has an equation that tells you what they should look like. On the other hand, that is a whole category of trying to fix things.
Yes. No. I mean, all of our papers float the word super Eddington somewhere in there, so it's certainly a possibility, which I like better than the idea that there's no accreting black hole there, which I find very hard to get my head around. So anyway.
So based on the image that you select the compactness.
Yeah.
Which means that the non-detection of the host galaxy so far.
No, it doesn't really mean that. Unfortunately, it's much more complicated because we definitely see starlight.
But the outside that.
It has to be within, so we have the one highly lensed source, which is smaller than 30 parsecs, but generally our size limit is 100. And I should be more precise, we actually do often see a little bit of fluff in the UV. So at 444, they are point sources, but the resolution is lower at 444. So they are smaller than 100 parsecs in the red. They tend to be around 100 parsecs fluffy in the UV.
My point is that there's an upper limit in the detection of the
yes,
outside.
Yes. This was the question about dust. Yes.
Yeah. So that the upper
None.
limit means that what's the host galaxy brightness? If you compare with a nearby galaxy, how dim the host galaxy is compared to the black hole?
If I assume that there's a low surface brightness component that I can't see, oh, excuse me, I knew that was going to happen. It's only been 250 days since I've done my software updates. Whoops, wrong thing. Okay. So the problem is that the JW data are really, really sensitive.
Yeah. That's why.
So, I think our sensitivity limits are more like 26 or 27, something like that, magnitudes per square arc second.
Sorry, I'm not the optical person.
So I have not gone down the rabbit hole of what kind of extended host galaxy could we hide, because I just don't think there could be enough mass out there to really change the story. Maybe, we say you can fit a few times 10 to the 9 in the core. Maybe you can triple that with some extended component. But it cannot be that these things have 10 to the 11 solar masses of stars that's missing. It's just impossible.
That would be our galaxy kind of galaxy.
You could probably get to 10 to the 10 if you really wanted to make them very dusty disks and just invoke, JWST dark. I mean, sure, you could do that if you really wanted to.
In terms of that, back to your introduction, Algorian relation, bulge and the black hole mass relation.
Yeah.
Where this goes to?
You mean if I boost the stellar mass by a factor of 10? Then they're only a factor of 10 above the local scaling relations. They're currently a factor of 100 above the local scaling relations. If you believe the black hole masses. If they're super Eddington, everything gets solved. Yeah.
So I'm curious, where does all this dust come from?
Which dust?
Red and
I mean, I don't think there's a problem. I think these ALMA people see plenty of gas and dust at redshift 7 already.
Well, I guess the question is, if you have that much gas and dust, can that explain is that consistent with the small stellar mass in these galaxies, in these systems?
Well, we have really, really dense gas. I didn't get into it, but we see Balmer absorption. Almost no AGNs show Balmer absorption. And to get that, you basically need Lyman alpha trapping so that the Balmer lines act like a resonance line. And so there's extremely dense gas in the inner regions of these, probably a bit outside of the broadline region because the velocities are pretty low. So they're like 200 to 400 kilometers per second. I don't think you need a large mass, but you certainly need very, very dense gas. And I mean, maybe that's not surprising because they're really small. Yeah.
So, I've been following little red dots for quite some time. And one of the
Well, it hasn't been that long. Come on.
He's still young.
It feels like a long time.
When I saw Jordy's paper, one of the first things that came into my head is like, we finally got a connection between the prediction from the X-ray studies about the high obscure fraction and what we're actually maybe seeing in the optical UV.
But then it turns out they're not detected in the X-ray.
Yeah, and the fact that we're seeing very broad H alpha with a very red continuum to me was screaming ISM absorptions, which a lot of the X-ray studies have been talking about. And one of the things that I was thinking about was whether these are actually related to the Seyfert 1.5s in the local universe, something similar at high redshift. Do you think that we're actually seeing some of the lower luminosity AGNs? I mean, they're probably lower luminosities.
So,
With high,
rest frame optically red luminous AGN have been selected before at redshift 2, both by Elad Glickman and Manda Banerjee. And those are all giant mergers. That's what they are. They're very intrinsically luminous. They have similar SEDs in the rest frame optical, but they all have hot dust.
yeah, okay.
And they're not point sources.
We're not seeing so much hot dust here.
Well, we haven't seen it yet.
At the very least, not so much.
Right. So, there are, at the minimum, 4 ALMA proposals to look for the other side of the hot dust peak for my monster. I know of at least 4 people who proposed to look at that.
What we really need right now is around 100 micron observations, right?
Yeah, that would be nice, yes. Yeah. Yeah.
I know. Sorry, I have like a series of questions because I also work on AGN. So, what is the contribution of the broad H alpha emission line to the bands?
We solved that by having a second color,
Okay.
which does not have line emission in it. So that's how we get rid of, if you don't do that, then you get a lot of star forming things with high H alpha or high O3 equivalent with.
Yeah, I was just thinking like the optical images, the images we're seeing are basically the H alpha emission from the emission?
No, most of them don't have the H alpha in 444.
Ah, okay. That makes sense. Just one thing could you comment on? No oxygen 3, very weak oxygen.
Yeah. So locally, things that are invoked to be super Eddington also do that. They don't have strong O3. And there's actually there's a lot of empirical observations of that over the last 40 years, but there's no physical explanation of it.
Yeah.
So I don't think it's a metallicity thing. I think it's an AGN phenomenology thing that no one understands.
Yeah, I was thinking about the host galaxy. Because even if you remove oxygen 3 from the AGN, there's still supposed to be oxygen 3 from the host galaxy if it starts forming. Or even oxygen 2.
Yeah, there's not a ton of ongoing unabsorbed star formation. If you want to invoke star formation, it has to be obscured. Yeah.
It has to be very obscure. So
Yeah.
we're definitely seeing a very dusty host galaxy in this sense. Could be a possibility.
Or there's not star formation.
Or there's no star formation.
Yeah.
So
We already have a pretty significant problem fitting all of those stars into 30 parsecs.
Very strong Balmer break.
Right. Yeah.
You say you don't like reionization, but I still want to ask.
So
they are really at redshift 7, 8, and they are.
these things don't matter for reionization.
With that kind of number density.
Yeah, even with the high number density, they turn out to not matter for reionization. So Pradika Dayal wrote a paper about this because we just had to work out the numbers, and the UV is so low. Even if you assume that there's regular UV coming out over some opening angle, and even if it's just basically a little bit too late. So most of reionization had to have already happened by stars. Maybe at late times the black holes contribute a bit. That was her conclusion.
If there are no more questions, Jenny will be here until around 4 or slightly before.
Probably slightly before, yeah.
So grab her after the talk if you are too shy to ask questions. Thank her again.
Thank you.